In this video, we'll look at formal charges and resonance structures. When we look at formal charges, what we're looking for is how we can draw the best Lewis structure possible. We've seen previously how to draw Lewis structures, but now we're going to look at which one is the best Lewis structure. So let's say we're told to draw the structure for the compound CnO. If you were to just draw this Lewis structure, you can end up with any one of our three structures drawn here. Now, when you draw any one of these three structures, technically, they're all correct. Technically, each one of them, as you can see, looking at the nitrogen, has an octet, carbon has an octet, oxygen has an octet. Same thing here. Nitrogen has an octet, carbon has an octet, oxygen has an octet. Even here, nitrogen has an octet, carbon and oxygen all have octets. So I fulfilled the octet rule and requirement for each one of these atoms, but only one of them we can consider the best Lewis structure. And for that, we're going to look at formal charge. What formal charge does is it assigns a potential charge to each atom. So kind of how much extra electrons does each atom have? If it has a formal charge that's negative, that says there's a lot of excess electron density around that atom. If it has a formal charge that's positive, that actually says that we've lost a little bit of electron density. It doesn't have as much electron density around it. You can almost think of formal charges as the molecular compound's way of coming up with the charge we would for something that's ionic. This kind of lets us know where the electron densities are. This one says there's a lot of electron density around nitrogen, not that much around oxygen. Here there's a lot of electron density, some electron density around nitrogen, carbon, oxygen, pretty good. Or here it says oxygen has a little more electron density versus carbon or nitrogen. So if we think about the electronegativity, that can give us a hint on which structure is the best. We know oxygen, it's closer to fluorine. Oxygen is actually a little more electronegative than nitrogen. So if anything, the oxygen wants the electrons more than the nitrogen does. So if I look at my three structures here, oxygen here is actually slightly positive, so it's electron deficient. That is a very unhappy state for oxygen. Here, electron's neutral and happy. Here, the oxygen's neutral and happy. Here, the oxygen actually has a little more electron density. It's okay with that. So if we had to pick between the nitrogen or oxygen, I would pick the oxygen to have the extra electron density. So I'd say this would probably be my best structure. Now, I'm sure you're asking yourself, how do I come up with the numbers on top? What are those numbers on top? Those are the formal charges. And there's a formula for coming up with our formal charges. To assign a formal charge, we're going to look at each atom, count the number of lone pairs, and half of the electrons it shares. So you can think we have our valence electrons. And if I look at the electrons assigned to oxygen, I have 1, 2, 3, 4, 5, 6. So since there's 6 electrons assigned, it gets a formal charge of 0. Now, if we're trying to figure out how everything's assigned, we can use a little equation. Our formal charge, that's going to equal our valence electron count. So how many valence electrons is it supposed to have? Minus the number of bonds it forms. So our number of bonds. So kind of minus the lines, minus the number of electrons in the lone pairs. So minus number of lone pair electrons. You can also think of formal charge as our valence electrons minus the lines we draw minus the dots. Easier way if you don't want to worry about figuring out number of bonds and number of lone pairs. Minus lines, minus dots. So our oxygen here, that has, since it's in column 6, 6 valence electrons. I have 2 lines, 1, 2, so 2 bonds. And then my number of lone pair electrons, 1, 2, 3, 4. 4 dots, 4 lone pair electrons. So 6 minus 2 minus 4 equals 0. Yay. We can even do it for something like this oxygen here. For that oxygen, we have 6 valence electrons minus 1, 2, 3 lines minus 2 dots, 1, 2. So 6 minus 3 minus 2 gives me a formal charge of plus 1. So that's saying this oxygen is somewhat electron deficient since it has a formal charge of plus 1. And we can see, figuring out for this oxygen, I have 6 minus 1 line, minus 1, 2, 3, 4, 5, 6 dots. So if we draw that out, that could be 6 minus 1 line minus 6 dots gives us a negative 1. So that's actually saying there's a little extra electron density around this oxygen. Whenever we're determining which structure is the best one, we want the least number of formal charges. We want everything to be 0. In an ideal world, we want everything to be 0. That means each atom is happy. Each atom has the exact number of electrons and the exact amount of electron density it wants. If we can't get to formal charge of 0 for everything, like our previous example here, then we'd want to put the negative charge on the more electronegative atom. So if I can't have everything 0, then, and I have to have a formal charge, then I want that formal charge to be on the more electronegative atom. So you can see we can easily use formal charges to figure out which structure gives us the best Lewis structure. And now, using this idea, we start doing what we call resonance and resonance structures. So if I told you to draw the Lewis structure for ozone, O3, you can end up with either the first structure here or the second structure. If we look at these two structures, what's different about them? Is there anything actually different? You can see the only difference is the double bond is on one side and then it switches over to the other side. The atoms are still in the same spots. I just switched which side the double bond got put on. Just switching the electrons around like this is what we call resonance. And what that means is all the atoms are still in the same spots, just the electrons kind of switched around. You can see here it went from 2 lone pairs and 2 bonds to 3 lone pairs and 1 bond. Here it's 3 lone pairs, 1 bond, to 2 lone pairs, 2 bonds. So resonance is just a different way we can draw the different Lewis structures. All the atoms are still in the same configurations, just the electrons have moved around. The electrons are slightly different. And when we look at that ozone and we actually examine the bond length, we find that the bond between the oxygens, so our bonds between our oxygens here and here, and here and here, they're the same length. So whether the double bond's on one side or the other, the length is the same. How can that be? When we have a double bond, that's more electron density, so that pulls the two atoms closer together. How could they be the same number? And this is what resonance actually teaches us. One Lewis structure may not be an accurate depiction of a molecule. Instead, multiple structures or multiple resonance structures better describe the molecule. So what's happening in real life is the electron, if we take our lone pair here and turn into a double bond, I can take the double bond and turn into a lone pair. That's what the arrows are representing. It's kind of the movement of the electrons. So if the electrons keep bouncing back and forth between the two oxygens, so that double bond keeps bouncing back and forth between atoms A and B, and then atoms B and C. When it bounces back and forth, it does it quick enough to where we can't detect an individual structure. Instead, we just kind of see the average of these two. And if we see the average of these two, that's how the bond length can be the same on both sides, even though technically the double bond might be in a different spot. It's going so fast and bouncing so fast between the atoms that we can't see that bounce. We just see kind of the average of it. So we really just see the average of the electrons going back and forth between these atoms. And this bouncing can occur with multiple atoms, not just three. So if I look at nitrate, a nitrate ion can be drawn as any one of these three. Since the nitrate can be drawn as any one of these three, we can call them resonance structures. So you can see that double bond is going between the top oxygen to the side to the other side. And it's kind of just spinning around between those three oxygens. So a more accurate representation would be if this double bond and those electrons are kind of going between all three of these oxygens here. But you can see with the resonance structure, I can take the electrons from the bond here and then move them up onto the oxygen. Then I can take one of these pair of electrons, one of the lone pairs, and move it to make another bond between this oxygen and nitrogen. And I'd end up with this Lewis structure. And we can do the same thing to go between the second Lewis structure and the third one. So again, if the electrons from that bond move up onto the oxygen, and one of the lone pairs moves down to make a double bond, I end up with the third structure. So resonance structures are really where you can find different Lewis structures. And if you can get different Lewis structures, but kind of alternate where a double bond is, then you have a resonance structure. And with our resonance structures, remember, the atoms are all in the same spot. The atoms don't change. Only the electrons move around. But everything still needs to fulfill its octet and still keep the same formal charges. But everything still needs to fulfill its octet here. We can think of this more as the electrons are delocalized. So if we go back to that ozone example, instead of drawing the two resonance structures, the electrons are really kind of smeared across all three atoms. That's what the dotted line represents, is the electrons are actually delocalized or spread over a few of the adjacent atoms. And so a couple things to remember when we're choosing the most important resonance form. The smaller the formal charge, the better. We always prefer smaller formal charges over larger ones. Ideally 0, because that's the smallest number, but if we can't have 0, as small as we can get. The same non-zero formal charge on adjacent atoms are not preferred. So you wouldn't want two atoms next to each other with negative formal charges. Instead, you might want a 0 or a positive next to a negative formal charge. And also, the more negative a formal charge, it should reside on the more electronegative atom. So like our first example, when we had to choose between nitrogen or oxygen, it's better to have the formal charge on the oxygen since that's more electronegative than nitrogen. And so now you guys should be able to calculate formal charges and also start to be able to draw resonance structures and use those formal charges to figure out which resonance structure is the best structure.